Good morning, students. I am your Nagini ma'am. Today I am going to give a good trick to find the metal deficiency defect problems, students. How to find the metal deficiency defect problems. This topic is from second PUC solid state lesson, students. So first of all, this metal deficiency defect. What is the metal deficiency defect? That means, students, in the here in this name only there is a meaning, students. That means there is a deficiency in the metal. Are you following? That means after the defect we can observe there is a deficiency in the metal, students. That is nothing but metal deficiency defect. Now this metal deficiency defect is belongs to non stoichiometric defects. What is stoichiometric defect, non stoichiometric defect? Okay na. So what is the difference between them? Now I am going to discuss you. I will give the one example, students. Okay na. So in that you can easily understand the what is the stoichiometric and non stoichiometric defect. And by using this a good trick, you can easily find metal deficiency defect problem, students. Those are NEET previous year questions, students. I want to discuss two questions, NEET previous year questions. There within fraction of seconds you can easily, within two to three steps, you can easily calculate that problem, students. You can easily find out that one. Okay, and after this explanation you will feel very easy, you will feel very better to answer that question, students. Okay, thank you very much, students. Listen this one. So what is the metal deficiency defect? Okay na. So first of all I'm going to discuss about the stoichiometric and non stoichiometric defect, students. Stoichiometric defect. See, students, so in the stoichiometric defect, students, I am taking first of all one crystal, NaCl crystal. Suppose AB is the crystal, students. In this crystal, I am taking this is A is one atom and B also one atom. Both are present in the 1:1 ratio, students. Here I can take example cesium chloride or lithium chloride. We can take any example, students. That means here cesium is one atom, chlorine one atom. That means 1:1, and lithium one atom, chlorine one atom. And also we can take NaCl, KCl, like that. That means they are present in the crystal only 1:1 ratio. Correct? Same ratio they are present. Correct? AB 1:1. Now this AB molecule, this crystal I'm multiplying with 100 atoms, students. This one A atom multiplying with 100, B atom also multiplying with 100. Then what you will get, students? It is converted into AB 100, B also 100. Are you following? 1 into 100, 100, 1 into 100, 100. So A atoms I'm taking 100, B atoms also I'm taking 100, students. Okay now. So before defect, students, equal ratio is there. That means AB, that means cation and anion, or metal and non-metal, both are maintaining the equal ratio. Correct? Equal ratio they are maintaining. Okay now. So after the defect, students, what they will get after the defect? If suppose from AB compound, two cations, suppose two cations, 2A plus and two anions, 2B minus. Are you following? Here two cations, A plus, B minus, anions, two anions we are removing. Okay now. So suppose AB compound, after the defect, what is happening, students? It lost two cations and two anions. Equal number of cations and anions are, it is missing, it is losing. Then what will happen, students? Here A becomes 98, then only 98 atoms will be present. In B atom, how many atoms will be there, students? Total 98 only will be. That means two cations, two anions are missed. That means two A atoms and two B atoms are missed. That means we will get A 98, B 9. Again we will get the same ratio, 1:1 ratio. Correct? That means before defect 1:1 ratio AB, after the defect also 1:1 ratio we are getting. So that means they are maintaining the same ratio before defect and after the defect. Are you following? Clear this one. So this type of defects we can observe, Nana, during the crystallization process, we know that. So here before defect, here AB compound is maintaining 1:1 ratio. After defect also 1:1 ratio maintaining. That's why these defects, or these compounds, will call it as stoichiometric defects. Are you following, students? This what we will call stoichiometric defects. These are stoichiometric compounds. These are stoichiometric compound, students, and these defects are calling as stoichiometric defects. Are you following? Now see, students, what is non-stoichiometric defect? Non-stoichiometric defect. What is the non-stoichiometric defect? See, students, here also I am taking one example. AB compound I am taking. Okay, now A is the metal, B is a non-metal, students. AB metal, AB is a compound. So here 1:1 ratio they are presenting. That means I'm multiplying with each atom with 100. So 100:100. Both are 100 atoms are present. Okay, now so here, if suppose this compound, if it is loses only cations, two cations, if it is losing, then what will happen, students? From A, 100 atoms are there total. After defect, it is losing two cations, so that's why it becomes 98. And B atoms are as usual. That means 100 atoms are present in B. That means here anions number is more, cations number is less. Are you following, students? So that means cations are A. So how many cations here? A cations are 98 only there, but B atoms are 100. That means A is which one, students? It is a metal. B atom is a non-metal. Are you following? This is a metal. So this one is metal, this one is non-metal. Are you following, students? That means here metal atoms are less. Are you following? After the defect, metal atoms are less when compared to the non-metal. Okay, now so that means we will call it as cation deficiency defect. That means two cations are less, or we will call it as two metal atoms are less. That's why we'll call it as metal deficiency defect. Are you following? So this what we will call, students, this one. This is nothing but metal deficiency defect. That means metal is less. How many metal atoms are less? Two metal atoms are less. Okay, now that means cations number is less than the anions number. Anions 100 are there, cations 98 are there. Are you following? That means metal atoms 98 and non-metals 100. Metal atoms are lesser than non-metal atoms. So that's why it is a metal deficiency defect. Are you following? This is metal deficiency defect. That means before defect they have the equal ratio 1:1, but after the defect, what happens, students? They are not maintaining the equal ratio. Are you following? That they are maintaining the different ratio, 98:100. Different ratio they are maintaining. So thus that type of compounds will call it as what we will call non-stoichiometric compound, students. Are you following? Non-stoichiometric compounds, they are not maintaining. We can take examples, students, here. What are the examples we can take? FeCl2 is iron chloride, iron oxide, correct or not? Okay, now so these examples we can take, students. Iron oxide and also nickel oxide. Okay, that means this type of defects, metal deficiency defect, where we can observe, students, maximum metal deficiency defect we can observe in the metals exhibiting the variable valencies. Are you following? Metals exhibiting the variable valencies. We know that example iron exhibiting the two variable valencies. One is +2 and two variable oxidation states, +2 +3. Variable valencies 2 and 3. Are you following? Because in the case of iron chloride, FeCl2 and FeCl3, iron is exhibiting +2 here. In FeCl3 compound, iron valency is 3. That means it is showing the two more than one variable valencies. Correct or not? So this metal deficiency defect, students, maximum, see here, metal deficiency defect, where we can observe, students, it deficiency defect is observed in the metal deficiency defect is where we can observe, students, it is observed in the observed in the where students, metals which are exhibiting the variable valencies. Clear? Exhibiting the metals exhibiting variable valencies. Are you following? Variable valencies. That means we know that iron, if suppose if I take iron, students, iron is showing the variable valencies 2 and 3. It can exhibit the variable valencies 2 and 3. Correct or not? So metal deficiency defect is observed in the metals exhibiting variable valencies. Iron is exhibiting variable valencies 2 and 3. Clear this one? So in these cases we can observe the non-stoichiometric defect or metal deficiency defect, students. Are you following? Now see, students, one general example I am going to discuss. See here, for example, in iron oxide I am taking, students. So generally iron oxide, oxygen, or what is oxygen oxidation state, students? It is -2. Iron oxidation state is how much, students? It is +2. Oxygen is -2, iron is +2. Now this crystal I am taking here, see here, Fe +2, okay, Fe +2, O -2, next Fe +2, O -2, again O -2, okay, O -2, Fe +2, O -2, Fe +2. Clear this, students? Okay. See, students, this is the iron oxide crystal. In this iron oxide crystal, suppose Fe +2 ion. Okay, now here one Fe +2 ion. If suppose Fe +2 ion is missing, students, that means during the crystallization process Fe +2 ion is missing. If it is one cation is missing, Fe +2 ion. Okay, now to maintain this electrical neutrality, students, to maintain the electrical neutrality, how many Fe +3 ions have to how many Fe +3 ions, Fe +2 ions should convert into Fe +3, students? Here see, one Fe +2 ion is there. Here Fe +2 ions. See, students, this is a general example. First you see this one, then you can understand this one example. See, students, this is a general example. I am taking A plus one cation, anion. So from this crystal, students, suppose A plus ion is, it is going outside. That means it is moves outside. Then what will happen, students? After the defect, what is happened? Here one cation is missed. That means here what is happened, students? Here one wire is formed. Correct? That means here cation, one cation is missed. That's why we'll get the one wired, one vacant. That means it is A plus ion cation. It is moving outside. That means it is moving from the lattice site. Okay, now so that means to maintain the electrical neutrality, what happens, students? Because of this A plus ion, another A plus ion, it is converted into A+2, students, to maintain the electrical neutrality. That means one A plus ion, if it is moved outside, that means if this crystal, if it loses one A plus ion, to maintain the electrical neutrality, what happens, students? This another A plus ion, any one A plus ion, it is converted into A+2, students. Are you following? See here, A+2. For example, here vacant wire is created, students. Here one wire is vacant orbital. That means one lattice site is will become vacant, students. This is B minus. Okay, now this one I am taking as A+2, B minus. This is as usual A plus, B minus, A plus. Okay, this A plus, B minus, A plus, B minus. Understood, Amma? See here, this one. See here, one A plus ion. So during the crystallization process, from this crystal one A plus ion is missed. So whenever one A plus ion is missed, to maintain the electrical neutrality, students, another A plus ion in this crystal, any one A plus ion, it is converted into A+2, students. Are you following? One plus is reduced now, so that's it. To balance that, another cation, it is converted into, students, +2. Are you following? following? It is converted into A plus 2. Are you following? Here one vacant lattice site is created. That means one wire is created, students. That means to maintain the electrical neutrality, in the place of one cation, whenever one cation is missed, another cation is converted into A plus 2 to maintain the electrical neutrality. Okay now, so that is nothing but here there is no change in the number of cations and anions. That means before defect how many are there, after the defect also same number of cations and anions will be there. Are you following, students? This is the thing. Next, see here, iron oxide I am taking, iron oxide. So here generally oxygen oxidation number is -2, students, and iron oxidation number is +2. Okay, now we know that iron is showing the variable valencies. So this is the iron oxide crystal, students, iron oxide crystal. Now see, students, in the iron oxide, one iron, suppose Fe plus 2 ion is missed from this crystal. Whenever Fe plus 2 ion is missed, here one wire is created. So to maintain the electrical neutrality, students, one Fe plus 2 ion is missed, then two Fe plus 3 ions. That means here this Fe plus 2, this Fe plus 2, both are converted into Fe plus 3 ions, students. Suppose in this crystal one Fe plus 2 one cation is missed, then in this crystal lattice, students, any two Fe plus 2 ions are converted into Fe plus 3 ions. Are you following, students? Fe plus 3 ions. Okay now see, students, here I will discuss. See, in this problem, here the composition of a sample of Wurtzite is Fe 0.93 and oxygen 1.00. What percentage of iron is present in the form of Fe plus 3? Asked, students. See this question, how to solve this one. See here, so in the last class, in the last topic what I discussed, students, here last example, here Fe plus 2, that means one Fe plus 2, here what happens, students, in the place of one Fe plus 2 is missed. That means in the crystal and any two Fe plus 2 ions are converted into Fe plus 3 to maintain the electrical neutrality. Okay now, see this one, here I'm giving the diagram. See, students, crystal lattice, this one. So one Fe plus 2 is lost now. See, students, these are the lattice sites. Okay, here which ions will be there? Here one Fe plus 2 ion is missed. So here one one wire is created. Okay, now one wire is created, and here this is generally iron oxide. Iron oxide, oxygen -2, iron +2. Both are in the ratio 1:1. Correct? 1 is to iron 1 atom, oxygen 1 atom. 1:1 ratio is there. Correct? See here which ions here. One Fe plus 2 ion is missed here. Correct or not? See here, once again I am discussing Fe plus 2, O minus 2, Fe plus 2, O minus 2, O minus 2, Fe plus 2, O minus 2, Fe plus 2, Fe plus 2, O minus 2, Fe plus 2, O minus 2. See this one here, this is the crystal lattice, students. So from this one Fe plus 2 ion is missed. Whenever one Fe plus 2 ion is missed, then what is happening, students? Here one is missed, then what happened? Here one wire is created. Are you following? And two Fe plus 2 ions are converted into Fe plus 3 ions. Are you following? See here, then it is converted into, again taking crystal lattice, students. See, students, now here whenever one Fe plus 2 is removed, then what will happen, students? Any two Fe plus 2 ions are converted into Fe plus 3, students, to maintain the electrical neutrality. Okay now, so that's why here this one it is converted into Fe plus 3. It is converted into Fe plus 3 ions. This is which one, students? Fe plus 3, Fe plus 3. Are you understanding? This is Fe plus 3 and this is also Fe plus 3. Clear this one? Fe plus 3, Fe plus plus 3. That means 1 Fe plus 2 when it is removed from the crystal lattice, then what will happen? 2 Fe plus 2 ions are converted into Fe plus 3 ions. Are you following? To maintain the electrical neutrality. Understanding, students? So 1 Fe plus 2 ions is removed from the crystal, then 2 Fe plus 3 ions are in the crystal. 2 Fe plus 2 ions convert into Fe plus 3. Are you understanding? So that's a finally what we can write, students, here. 1 Fe plus 2 ion is removed, then it produces 1 wired, and 2 Fe plus 2 ions are converted into 2 Fe plus 3 ions. That means to maintain the electrical neutrality, 1 Fe plus 2 ion is removed, then 2 Fe plus 3 ions are 2 Fe plus 2 ions are converted into Fe plus 3 ions. Are you following, students? 2 Fe plus 3 ions. So how to find it? See here, this problem, the composition of a, okay, so this formula you have to remember, students. From this formula we can calculate this problem, students. See here, what asked question, the composition of a sample of stite is Fe 0.93 oxygen 1, what percentage of iron is present in the form of Fe plus 3 asked. So here iron oxide given, actually iron 1 oxygen 1, it is 1:1 ratio, but here what given, students? 0.93, it is less than 1. That means there is a deficiency in the metal. That's it is a which one, students? It is a non-stoichiometric compound. Are you following? It is not showing the equal ratio, not maintain the same ratio, so that's it is a non-stoichiometric compound given. It is a metal deficiency defect. So they're asking question, what percentage of iron is present in the form of Fe plus 3 is asking, but actually here iron is which state? Oxidation state plus 2 here, but they're asking in the form of Fe plus 3 is asking percentage of iron. Okay, now see, students, iron oxide, it is just you multiply with 100, students. Here what given? Iron oxide. Okay, now iron oxide, just what given? 0.93 and 1.00 given, correct? This one, iron no oxygen. So this iron oxygen just you multiply with 100, students. Iron 0.93 given, it is multiply with 100, you will get 93. Oxygen already 1 only, multiply, when it is multiply with 100, you will get this is 100. How much you will get, students? 100 you will get. Before 1.00 given, when multiplied with 100 into 100, this one 0.93 into 100, 93 you will get. Just you multiply with 100, students, that values. Okay, now that means how many less, students? How many iron plus 2 kada? So generally iron plus 2 oxidation state, correct? That means here how many Fe plus 2 ions are removed, students? How many Fe plus 2 ions are lost from this one? 7. Correct. Here 93 given. That means how many Fe plus 2 ions are lost? 7 Fe plus 2 ions are lost. Correct or not? So 7 lost. Actually 1 Fe plus 2 ions lost means, okay, now how many Fe plus 3 ions are created in the crystal? 2 Fe plus 3 ions are created. But here how many lost? 7 lost. Correct. 7 Fe plus 2 ions are lost. So 7 Fe plus 2 ions are lost. Then how many Fe plus 3 ions are created, students? Each one is creating 2 Fe plus 3 ions. 7 Fe plus 2 ions are lost. So that means 7 Fe plus 2 ions creates how many Fe plus 3 ions, students? Total 14 Fe plus 3 ions it can create. Correct or not? Total 14 Fe plus 3 ions it is creating. Clear this one? Ions created. Clear this one? 14 Fe plus 3 ions are created. So that's a what is the how to find the percentage of iron, okay, now present in the form of Fe plus 3 is asking. So we have to find the percentage of Fe plus 3. So how to find it, students? Percentage of Fe plus 3 is asking. So how many created, students? Here 7 Fe plus 2 ions are lost. That's why how many ions Fe plus 3 ions are created? 14 Fe plus 3 ions are created. So 14 Fe plus 3 ions created by total how many given, students? How many Fe plus 2 ions are present in the crystal, students? 93 are there. Clear? By 93 into 100. Like this you have to find it, students. Are you understanding? understanding? See here, this just this one iron oxide given, Fe 0.93 into 1993 1.00 given. Oxygen 1%, oxygen is, it is completely 1 is there, but iron is, it is less than 1. So that's it, just you multiply these values into with 100, 93, 100 you will get. This formula just you remember students, you can find any problem students. Okay na? So 1 Fe plus 2 ion lost, then how many Fe plus 3 ions are created? 2 Fe plus 3 ions are created. That means here in the problem what given, how many lost iron Fe plus 2? It is losing 7 kada. 93 means 100 minus 93, 7 Fe plus 2 ions are lost, because in this compound iron oxidation state is plus 2 students. Okay na? So because oxygen oxidation state is minus 2 na, so that's why Fe plus 2. So Fe plus 2 ions, total 7 ions, 7 ions lost. So 7 ions lost means 7 Fe plus 2 ions are lost. Then how many they are creating students? 7 into 2, 14 Fe plus 3 ions are created. Are you following? That means per percentage of Fe plus 3, how to find it? How many ions Fe plus 3 ions are created by total number of Fe plus 2 ions? How many given students? 93 into 100. Then how much you will get students? 14 by 93. 14 by 93. See here, 14 into 100, 1400 divided by 93. Okay, 93. How much you will get students? 15.05. Answer is 15.05. This one answer. So here see students, what is the option is correct one here? Options, 4 options given. 15.05 means this option is correct. Are you following? So like this you have to find it students. So you have to remember only this formula students, then you can easily find it. You remember just 1 Fe plus 2 or 1 Fe plus 2 ion is lost means how many new Fe plus 3 ions are created? 2 Fe plus 3 ions are created. If suppose here 7 lost in the given problem, that means 7 into 2, 14 Fe plus 3 ions created. We have to find the percentage of Fe plus 3, then you will get 14 by how many created? 14 divided by total Fe plus 2 ions, how many are there? 93 are there, into 100 you will get this one. Understood students? Now see second problem. See students, the second problem. See here, the formula of nickel oxide with metal deficiency defect in its crystal, what given students? Nickel 0.98. What is the solution students? Nickel 0.98 given, oxygen 1 given. Are you following? It is 1 given. It is both are not in the same ratio, correct? This is 1, it is less than 1. That's why it is non-stoichiometric defect. It is a metal deficiency defect, because this is a metal, it is less than 1. So that's it is a metal deficiency defect. Are you following? Nickel 0.98 to 0, this is oxygen 1. Okay. Now see students, here actually nickel oxide, oxygen minus 2 oxidation number, nickel also plus 2. Okay, the nickel plus 2. So here plus 2 and this is minus 2 students. Now just you multiply with 100, then what you will get? Nickel 98, oxygen is 100, correct? Just you multiply with 100 students, these numbers. You will get this one. That means here nickel, how many lost students? 98 given. That means 2 cations lost, 2 metals lost. That means there is a deficiency in the metal 2 metals, there is a deficiency. Okay na? That means one metal, how many creating students? Here nickel is there, here nickel given, here also Ni plus 2 kada, here iron I discuss in the, just you remember one Ni plus 2 ion, if it lose, okay na, 1 Ni plus 2, okay na, if it is lost, one wire is created, and how many Ni plus 3 ions are produced students? 2 Ni plus 3 ions are produced. Are you following? Same formula. In the case of iron, you are taking like this. In the case of nickel, what we have to take students? 1 nickel, 1 Ni plus 2 lost, 2 Ni plus 3 ions are created. Are you following? 2 Ni plus 3 ions are created. So remember this formula students. Now we have to find the which one students? The fraction of nickel existing as Ni plus 2 is asking. First I will go to calculate students Ni plus 3. Here Ni plus 3 percentage I will calculate. Then I will go to the two problems I will discuss, students. Here they're asking only the fraction of nickel in the form of Ni plus 2 is asking. Okay na? I'm going to calculate Ni plus 3 also. Okay na? What is the percentage of Ni plus 3? Okay, that question also I'm going to calculate. See students, here percentage of now see here how many cations are lost, students. Two cations are lost, correct? Two metals are less. Understanding? One lost means how many Ni plus 3 created, students? 2 Ni plus 3 created. 2 Ni plus 2 lost means how many they will create? 4 Ni plus 3 ions are created. Are you following? 2 Ni plus 3 ions are created. Okay, now how to find the percentage, students? How to find it? How to find the percentage of Ni plus 3? See here, percentage of Ni plus 3, how to find it? So percentage of Ni plus 3 is equal to what we can write, students? Percentage of Ni plus 3. How many created, students? 4 Ni plus 3 ions are created. Total how many Ni plus 2 given, students? 98 given. So 4 by 98 into 100, students. Okay now. So then they will get the percentage of the Ni plus 3, students. See here, 400 by 98. Correct? 400 by 98. How much, students? 4.08. How much, students? 4.08 percentage you will get. 4.08. Understood? This is the percentage of Ni plus 3, students. Okay now what in the question they're asking, students, Ni plus 2, what is the fraction of Ni plus Ni existing as Ni plus 2 is asking. So in the form of Ni plus 2 they're asking fraction of nickel. Okay now, so I'm going to calculate the percentage of Ni plus 2, students. See here, this is Ni plus 3 I calculated. Suppose I want to calculate Ni plus 2 percentage also. Percentage of Ni plus 2, how to find it? Ni plus 2. See here, total here how many created Ni plus 3? 4 na. We are calculating Ni plus 2 percentage. Are you following? For Ni plus 2 percentage I'm going to calculate. So total 4 is there here. 4 Ni plus 3 created. So actually Ni plus 2 how many given, students? 98 given. Are you following in the problem? 98 given. So 98 minus 4. How much, students? You have to first you have to subtract 98 minus 4. How much, students? 98 minus 4 means 94 you will get. Only Ni plus 2 ions. So 94 by how many Ni plus 2 ions given, students? 98 into 100. Are you following? 94 divided by 98. 94 divided by 98, okay, into 100. 94 divided by, once again, students, 9400. Okay, 9400 divided by 98. How much, students? 95 point, how much answer? 95.91 percentage there. But question they are not asking percentage, students. Okay, this model, two cases also I discussed you. But what is the question? The fraction of nickel is asking. Only nickel in the case of Ni plus 2 is asking. So what is the fraction of nickel? So question is only fraction is asking. Fraction of Ni plus 2 is asking. Okay, Ni plus 2. Then how to find it? Only this value had to take. Fraction of nickel means only this one. That means 94 by 98 only you had to calculate. How much, students? 94 by 98. 94 divided by 98. How much, students? 0.959. That means it is approximately equals to 0.96. Are you understanding? So this is the fraction of Ni plus 2, students. Clear this one? Okay na? So this is the second problem. Understood, students? Here question is the formula of nickel oxide with metal deficiency defect, this one given, Ni 0.98 oxygen. Okay, that means it is a metal deficiency defect. So as it is, I am taking Ni 0.980 oxygen. But nickel oxide if I take oxygen oxidation state -2, nickel is +2. Both are in the same ratio, 1:1 ratio, correct? But here in the question they given 0.98, this is 1. That means there is a less than 1, correct? Metal is less than 1, that is it. That means that's why we'll call it as metal deficiency defect. Okay, how many it is lost, students? 2 atoms lost. But actually one atom is lost, then how many Ni plus 3 created, students? One Ni plus 2 is lost. Its oxidation number +2 kada, Ni plus 2. So one Ni plus 2 lost means one Yod is created. That means 2 Ni plus 3 is created. Are you following? 2 Ni plus 3 created. This formula you have to remember, students. Then here how many, one lost means 4 created. Here one lost means 2 created, but in the question 2 lost na, 98 there, 98 given. So that means 2 lost means 2, how many created? 4 created. So what is the percentage of Ni plus 3? 4. The number of created Ni plus 3, the number of Ni plus 3 ions created by total number of Ni plus 2 ions are present in the crystal, 98 into 100, then you will get. And next, percentage of Ni plus 2, how to find it? Ni plus 2 means here total how many created? Ni plus 3, 4 created, total 98. This value are 98 is Ni plus 2 ions, this is Ni plus 3 ions. Are you following? So how many Ni plus 3 ions? 4 are there. You have to subtract from Ni plus 2, you will get this value. So that by total Ni plus 2 ions into 100, you will calculate like, you have to calculate like this, students. Understood, Amma? So Ni plus 3 we calculated. Ni plus 2, percentage of Ni plus 2, how to find it? It is a one model, and there is another model also, students. How to find it? Percentage of Ni plus 2. So percentage of Ni plus 2, how to find it means 100 minus percentage of Ni plus 3. Okay na? So 100 minus percentage of Ni plus 3, how much, students? 4.08 percentage, correct? This one you have to find it. So 4.08, then you will get answer is 95.91%. This is the second model. Are you following? To calculate the percentage of nickel, Ni plus 2. Are you following? Ni plus 2. This is also second method. Are you following? This is the first model. Clear this one? So like this you have to find it, Ni plus 2. So first you have to subtract 98 minus 4, then you will get 94 by 98 into 100, this one. But the question is fraction of Ni plus 2 is asking, only fraction, this one you have to take, answer it will get. Okay, thank you very much, students. I hope you like this video. Thank you very much. Please subscribe my channel, students.